Okay, MAPers, the third video here is on statistics, chapters 3 and 4. Chapter 3 was mostly on scatter plots and lines of best fits. We used the TI-83 and not, both. Um, and then in chapter 4 was all that stuff on statistical literacy, lots of definitions and that sort of thing, but there were also a few calculations, and we'll see some of those in the examples. So let's get at it. Oops. FERD goes to every third classroom and surveys every 10th student. Here's FERD's data. And as we'll see soon, FERD actually made a blunder, a mistake, as FERD does often when he recorded this, but we'll talk about that later. What type of sampling techniques is this technique? Remember, we talked about a bunch of different ways to get the data. And when we go sort of every other person or every third person or every 10th student, that's systematic. Because it's kind of like we're planning on a system, right? And these definitions you'll have to remember. If we just put everybody's name in a hat, that's called simple random sample. If we survey everybody, that's called a census sample. If we, want to select an equal or a representative number of males and females, or grade 9s and grade 10s, that's called a stratified sample. Stratified. And, there are these definitions. You might want to include those definitions on your cheat sheet if you get some room. Not going to be a lot of definitions on here. A question like this is very typical of our exam. Systematic. There are 800 students at FERD school. How many should he survey to get a representative sample? Well, remember, our textbook says 10%. So it's just 10% of the 800. 0.1 is 10% as a decimal. Of means times, and that's 80. And so again, the fact that for a representative sample we should have 10%, that could go on your cheat sheet if you wanted to. I'm not an example, so you couldn't write down these examples, but you could write down that fact. Representative sample, 10% of the population. And notice, he should have surveyed 80, and good old FERD, he surveyed 7 people. Find the quartiles for the marks data. Well, this is the marks data here. And the idea to find the quartiles, this was one of the calculations in chapter 4, is we put them in order. We write them in order. Should have wrote this out beforehand so you're not watching me write. And then there's 2 steps. First of all, we find the median. The median is the halfway point in this case because they're all written out. There's the median right there, right? And since there's an odd number of pieces of data, there's 3 before, there's like 3 in the first half, there's the median, and 3 in the second half, and we call that Q2. It's also called the median, right? The middle piece of data. And then we find the median of the first half of the data. So if I cover up this second half of the data, including the median, there's Q1 right there. That's the first quartile. And then I cover up the first half of the data and I do the median of the second half of the data, there's Q3. So my first quartile is 56, Q2 is 66, and Q3 is 80. And then these together are the quartiles. There, good. The second question, it says create a scatter plot, so we're going to do that. I'm actually going to pause the video and set up my my axes so you don't have to watch me do that. Okay, I've plotted my data, and I'm going to point out a few things. First of all, this is where FERD made a major blunder. He put mark as the first thing, as if, somebody gets 56, that's going to cause them to work 3 hours or 0 hours or whatever. These two should be switched, right? It should be we would guess that the hours worked is causing the marks, right? If you work too many hours, you're going to get low marks or whatever it is. And so, in fact, the way Ferd collected this data, I think he was wrong. These two should have been switched. This should have been the x variable, and this the y variable. And I actually did that, right? So I put hours worked is causing marks to change. And so I did a plot. Notice that I put a break in the graph here, and then did a plot, and did my scatter plot. And what's funny, the general trend, because I mean the next thing we need to do is find the equation of the line of best fit. We need to draw a line of best fit. The idea here, maybe red I'll do too, was to kind of put a loop around it. If you're not very good at this, this is a nice piece of advice, is put a loop around that. And then your line of best fit is supposed to cut this in half, right? Cut this loop in half. Oops. Maybe something like that. Something like that. Anyway, and then we pick two numbers that are on or close to on our line of best fit. Maybe that's not a very good line of best fit. Split it in half here. How does that look? That looks maybe a little bit better. And notice that what this trend shows, this is opposite that we would expect. The more hours you work, the higher your mark is. Maybe it's because you're a more organized person or something like that. Who knows? But how we calculate the line of best fit, I'm going to show you two ways. So be patient about this. And I'm going to pick 2 points that are on or close to on the line. This is sort of the pencil and paper style. This line I'm going to pick, which point I'm going to pick. And it doesn't matter what point you pick, but they're going to be on or close to on the line. So I'm going to pick that point right there as well, which is the point 12 hours worked and an 80% average. And then I'm going to use those points to calculate the line of best fit. Remember, it's y equals mx plus b. M, a little slope. All these are formulas that should be on your formula sheet, right? y2 minus y1 over x2 minus x1. Put those numbers in there. Remember, y2 minus 56 over x2 is 12 minus 3. This is the rate of change as well. Later on, we'll call this the rate of change. And that is about 2.67. And so that means the m is 2.67. And if we, it looks like, if I just look at the line of best fit, it looks like my y-intercept is around 44-ish. And so I could, if I'm lazy, just write in 44 for B, but I'm actually going to go through the calculation because there's sometimes, like if we put a break in the graph here, in the x graph, or in the x-axis, that we can't use it. So I'm going to just calculate what B is, show you how that works again. X was 12 plus B, and then I can calculate what B is, right? This is X and that's Y, and I could have used the other point. It really doesn't matter. And then I do this calculation. 2.67 times 12 is 32. Subtract 32 from both sides. I get B is 48. And notice that that's pretty close to what we would have got straight from reading in the graph, but not always do we have that. And then the line of best fit is 2.67x plus 48. And the idea is the line of best fit allows us to make predictions. So say if you worked 7 hours, well then I can put in 7 for x and calculate what my mark should be. A second way to do this, and so on an exam, if it doesn't say which way to do it, you could do it this way, or you could use the calculator, right? Now, The graphing calculator will be sitting on your desk. Remember, if you got any junk there, whatever it is, you just stat 1 for edit, and then I put the data in. Notice I switched the order of the table because we said that Ferd blew it, that hours worked should be first and then mark should be second. And then once you get all the data in, it's pretty easy to get the line of best fit. You go stat, calc, and then lin reg. And remember, there's the quadratic reg for other curves and stuff. We've got exponential regression for all those exponential functions, and so on. We could do other regressions if we wanted to. This one's just a line of best fit. So I'm going to press enter. If I press enter again, then there's my line of best fit. And notice how close it is. So I'm going to pick a different color, and maybe not very much choice in colors on this one. So over here I'm going to write TI-83, and notice you don't have to do both terms. You don't have to do both kinds. You could do either pencil and paper or TI-83, but if you use the TI-83, make sure you tell me that you did that. So y equals I'm going to say 2.06 2.06x plus 51 it was. 51.6. Almost 52. So we were pretty close. That's a TI-83, and of course that's all the work you'd have to show. TI-83, there's your equation of line of best fit. One thing that you might be worried about, no R's, right? And that's one way to decide which is the best curve. And how we get the R to show is second catalog. We've got to scroll down to this diagnostics business. Again, steps for your formula sheet, right, folks? Diagnostics on, and then I'd have to do stat, calc. I have to do linear regression again, unfortunately. But it'll give me the same answer, and my R value, an R value of 0.86, it means it's a pretty good model, right? And then that's what's called the correlation coefficient. That tells me that I've got a pretty good model. All right, this video is getting long, but we got one more little example to do, and then off we go. What does 2002 mean? Well, 2002 is the base year. So whatever we're measuring for the price index, in this case it's driver's licenses, they calculated it, and then all the percent changes, they go back and they compare to 2002. So if it was, maybe it was $50 in 2002, and if it goes up a few dollars, then they can figure out the percent change, and they compare back to 2002 being like 100 points or 100%. So the base year was 2002. So all the calculations are compared back to the price in 2002. Estimate the rate of change. This is slope, isn't it? So what we did is we, over the 10 years shown, we take those 2 points. It looks like it's almost 100, but we'll say it's not. That point looks like it's the year 2000, and maybe 95, we'll say. And this is the point 2010, and I don't know, 150? That's pretty close to 150. And so the rate of change is rise over run, and you're welcome to use rise over run or y2 minus y1 or whatever, is 150 minus 95 over 2010, subtract 2000. Jam that into a calculator, and you get about 5.5 points per year. And it's not percent, it's points per year. Okay, what else we got? Easy peasy. What was the percent increase? Well, this is what these indexes, the indices are all about. What was the percent increase from 2004 to 2005? So we saw in 2004 it was there. 2005 it was there. What's the percent increase in there? That's for question C. And remember, there's a little formula for these percent increases, and it's new minus old over old, right? It's not quite rate of change, new minus old over old. Well, the new value, the 2005 value was, this is estimate, right? It'd be 140 over the old value, which was maybe 110. And then I calculate that, and ends up to be about a 27% increase. So in that 1 year, from 2004 to 2005, was a 27% increase in driver's license costs, which is a little bit shocking. Notice what's nice about index values, if we want to compare back to 2002, the price in 2005, from 2002 to 2005, since this represents 100%, we can see 40% increase since 2002. It's only a 10% increase to 2004, right? Because this is value of 210. So in those 2 years, it was only a 10% increase. It's easy in indices to compare to the base value, but when it's not 2 years that aren't the base value, we have to use the new minus old over old formula. All right, that's it for chapters 3 and 4. Chapters 5 and 6 are next, which are our modeling chapters, graphical modeling and algebraic modeling.